Our introduction to chemical kinetics. Chemical kinetics is the study of reaction rates and how quickly reactants are consumed or products are formed. It focuses on the speed at which chemical transformations occur. Reaction rates measure the change in concentration of reactants or products over time. As a reaction proceeds, reactant concentration decreases while product concentration increases. The rate can be expressed mathematically as the negative change in reactant concentration or the positive change in product concentration over time. Reaction rates are typically measured in units like moles per liter per second, which we write as mol for Ls. These units reflect the change in concentration over time. Other common units include moles per liter per minute, or simply molar per second. Understanding reaction rates is crucial in numerous fields. In industrial processes, kinetics helps optimize reaction conditions for maximum efficiency and product yield. In biological systems, kinetics is essential for understanding enzyme catalysis and metabolic rates. And in everyday life, kinetics explains phenomena like food spoilage, rusting, and pharmaceutical shelf life. It's important to distinguish between thermodynamics and kinetics. Thermodynamics tells us if a reaction is possible, focusing on energy changes and equilibrium positions. Chemical kinetics, on the other hand, tells us how fast a reaction happens, focusing on reaction mechanisms and the rate of approach to equilibrium. In summary, chemical kinetics helps us understand not just if a reaction will occur, but how fast it will happen. Rate laws are mathematical expressions that describe how reaction rates depend on the concentrations of reactants. The general form of a rate law for a reaction between reactants A and B can be written as rate equals K times the concentration of A raised to the power m times the concentration of B raised to the power n. In this equation, K is the rate constant specific to the reaction. M and n are the reaction orders with respect to reactants A and B. The overall reaction order is the sum of these individual orders. Reaction orders are determined experimentally by measuring how reaction rates change when reactant concentrations are varied. Let's analyze an example data set. In these experiments, we vary the concentrations of reactants A and B and measure the initial reaction rates. To determine the reaction orders, we compare experiments where only one concentration changes at a time. From experiments 1 and 2, we see that when we double the concentration of A, the rate increases by a factor of 4. This indicates that the reaction is second order with respect to A. From experiments 1 and 3, we see that when we double the concentration of B, the rate doubles as well. This indicates that the reaction is first order with respect to B. Therefore, our rate law is rate equals K times A squared times B. The rate constant K is not truly constant, it depends on temperature. This relationship is described by the Arrhenius equation, K equals A times e to the negative EA divided by RT. In this equation, A is the frequency factor related to collision frequency, EA is the activation energy, the energy barrier that must be overcome for the reaction to proceed. R is the gas constant, and T is the absolute temperature in Kelvin. The activation energy is represented in this energy diagram. As temperature increases, more molecules have enough energy to overcome this barrier, resulting in faster reaction rates.